Welcome back to The Explainer. So today we're diving into a document that completely fundamentally rewired how we understand the universe. We're looking at Albert Einstein's mind-bending paper published in September 1905. It's honestly kind of wild. This thing is just 3 pages long translated, but it literally shattered the boundary between the physical stuff we can touch and the unseen energy all around us.
Let's jump right in. The literal title of this super short paper is actually a question. Does the inertia of a body depend upon its energy content? It sets up this perfect intellectual detective story. I love this because he doesn't just come out and declare a new law of physics. Instead, he poses a puzzle. He's asking, hey, does the actual mass of an object, its resistance to being pushed around, its inertia, does that have a direct mathematical link to the amount of energy stuffed inside it?
Now, to solve this puzzle, Einstein didn't go lock himself in a lab with scales and glowing green rocks. Nope, he used pure logic, the established Maxwell-Hertz equations for empty space, and one absolute rock-solid rule, the principle of relativity. Basically, this principle says that the laws governing a physical system don't change based on which coordinate system you use to look at them, as long as they're moving steadily relative to each other. It's the absolute linchpin of his whole argument. Physics has to work exactly the same whether you're standing totally still or coasting by on a super smooth train.
To actually use this principle, we need to cut through the jargon a bit and set up our 2 different points of view. First, we've got the stationary view. Think of this as standing on the platform, your physical body is completely at rest. Then we have the moving view. Einstein uses these fancy Greek letters, C, eta, and zeta, but basically, this view is just cruising along parallel to the first one at a constant, steady speed, which we'll call v. We're going to watch one single event play out from both of these distinct perspectives.
And here is the beautifully simple thought experiment Einstein used to finally bridge that gap between mass and energy. Step 1, we take that stationary body. Step 2, the body suddenly shoots out plane waves of light in exactly opposite directions at the exact same time. Step 3, we just measure the energy of the body before and after it flashes that light. Since the light shoots out equally in both directions, the body doesn't get kicked backward or forward, right? It just stays perfectly still in that stationary system.
Okay, let's look at the math for that stationary system. The initial energy is going to equal the remaining energy, plus the light it just gave off. Now here's a fun little piece of historical trivia for you. Einstein originally used the letter L to represent the energy of light. I guess he wanted to keep us on our toes, because obviously today we'd all expect an E. But basically, as the math shows, the original energy just splits itself between the body and those 2 opposite beams of light.
So what happens when we watch that exact same flash of light from the moving system? Well, because we're moving at velocity v relative to the light, the energy actually looks different to us. When we factor in c, the speed of light, that relative motion basically causes the total energy of the light to stretch out mathematically. It literally becomes larger than it was in the stationary view.
And here is where the detective work gets so clever. Einstein decides, all right, let's subtract the stationary equations from the moving ones. But what does that difference actually mean in the real world? Well, since the body is sitting still in one view and moving in the other, the difference between them is really just the kinetic energy of the body, its energy of motion, plus some arbitrary constant that we can honestly just ignore. The crucial thing is that that constant doesn't change at all while the light is being emitted.
Right, so by tossing out that unchanging constant, we land on a really remarkable mathematical truth. This new equation proves a massive, game-changing point. The kinetic energy of the body actually drops. It gets smaller just because it emitted light. And the exact amount of that loss, it's dictated purely by the light itself and the speed of light. It is totally independent of the body itself.
Honestly, that equation is looking a bit messy at this point. So Einstein pulls a bit of a mathematical magic trick. If a body is moving way slower than the speed of light, which, let's face it, most things are, the value of v over c is tiny. So, by expanding the equation and ignoring the magnitudes of 4th and higher orders, which is just a fancy way of saying he trimmed away the microscopic fractions that don't really matter for a slow-moving body, he simplifies the algebra to reveal something absolutely incredible.
Seriously, this is the climactic moment of the whole paper. By cleaning up that math, the kinetic energy difference gets isolated into a format you might actually recognize. The change in kinetic energy simply equals 1/2 times L over c squared times v squared.
To really appreciate what just happened here, look at how perfectly this new equation mirrors the standard classical formula for kinetic energy. I mean, every high school physics student learns that kinetic energy equals 1/2 mv², right? Where m is mass. Einstein's new derivation is exactly the same shape.
He literally just swapped out the mass variable, m, and replaced it with energy divided by the speed of light squared, or L over c squared.
So what's the big deal? The crucial point is this. If a body gives off energy in the form of radiation, which remember is our L, its actual mass physically shrinks by L divided by c squared. The fact that the energy withdrawn from the body turned into radiation doesn't matter at all. The actual physical mass of the body itself fundamentally decreased just by releasing energy.
Which brings us directly to this absolute mic drop quote from the text. Just listen to Einstein's exact, triumphant conclusion here. The mass of a body is a measure of its energy content. Boom. With that one single sentence, Einstein officially birthed the most famous scientific concept in human history. Mass and energy, they are not two separate, completely unrelated properties of the universe. Mass literally is just a measurement of how much energy is locked up inside an object.
And to make this completely concrete, Einstein gave us the exact mathematical conversion rate. And it is a staggering number, 9 times 10 to the 20th power. He essentially stated that the energy changes by L, measured in ergs, the mass changes by L divided by 9 times 10 to the 20th, in grams. Meaning a tiny, practically invisible change in mass correlates to an astronomically massive amount of energy. Now you might be wondering, where is the famous equation? Well, as the source text points out, E equals mc² doesn't actually show up printed exactly like that in the 1905 German text. But the entire concept is right there. Einstein wrote that mass diminishes by L over c squared. In an equation, that's m equals L over c squared. If you simply take his quirky L and swap it for our modern E for energy, you trivially arrive at the iconic E equals mc². It is the exact same mathematical reality, we're just using our modern alphabet.
Now, Einstein was definitely a theorist, but he wanted his work proven in the real world for sure. He actually predicted in this very paper how we could put this to the test. Since the speed of light squared is such a gigantic number, everyday objects just don't lose enough mass when they give off energy for us to ever notice it on a scale. So he pointed out that we'd need to test this on bodies with highly variable energy content. He specifically called out extremely radioactive materials, like radium salts. Because they're constantly shooting off massive amounts of energy, you could eventually measure the tiny corresponding loss in their mass.
The final thought he leaves us with in the main text is just wild. If the theory corresponds to the facts, radiation conveys inertia between the emitting and absorbing bodies. And honestly, this is exactly why this matters to you and how we understand reality itself. Mass and energy aren't separate things. They're essentially two different masks worn by the exact same physical reality. When a beam of light travels across the room and hits your skin, it is literally conveying inertia, the most fundamental property of mass, through empty space.
We're going to wrap up the explainer today with a thought to take with you. If mass is really just extremely concentrated energy, locked up and waiting, what unimaginable power is hiding inside the ordinary, everyday objects sitting all around you right now? I mean, even a simple paperweight on your desk contains a literal universe of energy, hidden away simply because it's at rest. It is a totally transformative way to look at the physical world, and it all came from 3 pages of pure, elegant logic. Thanks for joining me on this deep dive into Einstein's masterwork. Keep questioning and keep exploring.